Right now, as you watch this, a piano-sized spacecraft is drifting more than 60 astronomical units from Earth, so far away that sunlight is roughly 3,600 times weaker than it is in your backyard, and a radio message needs over 8 hours just to say, hello. What if I told you that same spacecraft, New Horizons, still has enough brainpower, enough power, and enough stubborn engineering to do real science out there, beyond Pluto, in a region where the solar system stops feeling like a place and starts feeling like a question? Stay with me, because one of the things New Horizons keeps hearing should have faded into silence a long time ago, and it hasn't. Here's where it gets crazy. New Horizons is moving at around 14 kilometers per second, in a deep freeze, in near-permanent night, surviving on a plutonium battery that loses a little bit of power every year, only a few watts, but out there, a few watts is the difference between, we can run an instrument, and, we go to sleep. It can't unfold a solar panel. It can't pull into a pit stop. It can't call for a repair crew. And the farther it gets, the thinner the data pipe becomes, sometimes just a few kilobits per second, meaning a single high-quality observation can take hours to send home. Yet it keeps returning measurements that refuse to behave. Impossible fact number 1, at 65 AU, the Sun is basically a painfully bright star. It still rules the sky, but it barely pays the power bill for physics. Impossible fact number 2, the outer solar system is not supposed to be busy. In the clean version of the textbook, things thin out, smooth out, quiet down. Impossible fact number 3, New Horizons keeps finding hints, dust counts that don't drop off like you'd naively expect, particle environments that look structured, and even faint background sky measurements that sparked serious debate among scientists who do this for a living. So what is it actually flying through? And why does the edge of the Sun's influence look less like a neat border, and more like weather? To make sense of the weirdness, we need the normal story first. The Sun doesn't just shine, it blows. The solar wind is a stream of charged particles pouring outward, dragging magnetic fields with it, inflating a colossal protective bubble around the planets called the heliosphere. If you want a mental image, don't picture a glass sphere. Picture a campfire's hot breath pushing into cold night air. Close to the fire, everything is turbulent and loud. Far away, you'd expect calm, less heat, less motion, less drama. Eventually, you reach the place where the fire's breath can't dominate anymore, and the surrounding night pushes back. That boundary region is where the heliosphere gets complicated. New Horizons is one of the few spacecraft that can sample that far-out environment from a fast, clean trajectory through the Kuiper Belt. It carries a set of senses for the frontier. SWAP measures solar wind ions, Pepsi measures higher energy particles, and the Venetia Burney student dust counter does something beautifully direct. It counts tiny dust impacts like a Geiger counter counts radiation. And then there's the eyes, cameras that, among other things, can stare into deep space and help measure how bright the background sky really is when you're far from the inner solar system's glare. So here's what should happen as you leave the planets behind. Sunlight drops as the inverse square of distance. Goes 60 times farther from the Sun, and the light is 60 superscript 2, 3,600 times weaker. The solar wind should also weaken with distance, becoming less dense, less forceful, and, in a simplistic view, less interesting. Dust? You might expect it to thin out too, fewer collisions, fewer particles, more emptiness. And the deep sky, if you subtract out stars and known galaxies, should look about as uniform as it ever gets. This is where things get strange. Some New Horizons measurements don't simply fade into a quiet, predictable background. Instead, the outer heliosphere and Kuiper Belt environment look textured, layered, structured, sometimes stubbornly persistent. And that forces a new question: is the frontier weird because space is weird, or because we've been modeling it with the wrong kind of simplicity? Now, a quick pattern interrupt. If you're picturing New Horizons like a sleek sci-fi ship confidently cruising into darkness, flip that image. It's more like a marathon runner who can't stop running, even as the air gets thinner, because stopping means freezing. Every observation is a trade, power, time, data volume, pointing constraints. And the most interesting science is often the hardest to do when you're far enough out that every watt and every bit matters. The story starts like a clean success and then turns into a mystery. New Horizons launches in 2006, a bullet aimed at the outer solar system. In 2015, it performs the Pluto flyby, one chance, one trajectory, one set of images that instantly rewired our sense of what a planet at the edge can be. This is Alan Stern's team at Southwest Research Institute, mission operations at Johns Hopkins APL, and a long list of scientists and engineers who had to make a spacecraft hit a moving target billions of kilometers away, with no do-overs. Then in 2019, it nails Arrokoth, a Kuiper Belt object so primordial it looks like two gently merged lobes, evidence that early solar system building blocks could assemble softly, not always through violent smash-ups. After that, no glamorous flybys lined up. Just a long, outward glide. And that's when New Horizons quietly becomes something else, not a tourist camera, but a field scientist. It starts taking the kind of measurements you only appreciate if you care about invisible things, dust grains the size of smoke particles, sparse streams of ions, the faint glow of background light after you subtract the obvious stuff. Here's the detective part, the dust counter keeps ticking. Not like a storm, more like a steady tapping, as if the spacecraft is moving through a thin, persistent haze of microscopic grains. On its own, that might not sound dramatic. But stretch it over years. Year after year. Distance after distance. A long baseline turns, maybe, into, this is a real environment. Meanwhile, SWAP and Pepsi keep sampling charged particles shaped by the sun and by whatever the heliosphere is running into. And the readings look less like a single smooth fade and more like an evolving, structured medium, almost like the solar wind has a memory, carrying the imprint of solar activity outward, delayed and distorted. Cliffhanger moment, if the heliosphere is a bubble, why doesn't the bubble's skin behave like one? Why do some signatures look wrinkled, layered, or unexpectedly persistent? Stay with me here, because the best way to think about it is with three competing explanations, three theories that each feel convincing, and annoyingly, all three can be true at the same time. Theory 1, the solar cycle, stretched across the solar system. The sun doesn't blow the same wind every day. It goes through cycles of activity, more eruptions, fewer eruptions, stronger winds, weaker winds. Those changes propagate outward like ripples, but not like perfect circles in a pond. They get smeared, mixed, and reshaped as they travel. By the time those ripples reach 60 plus AU, you're seeing ancient solar weather, conditions from years ago arriving late, colliding with other waves, forming compressions and rarefactions. In that picture, New Horizons isn't just measuring distance. It's reading a time capsule of the sun. Theory 2, the Kuiper Belt is dustier than the simple story. Not a thick fog you could see, nothing like that. More like the faintest sandblasting, spread across a huge volume. The Kuiper Belt is filled with icy bodies, and over long timescales, collisions happen. Even gentle impacts can shed grains. Radiation forces and plasma effects can shepherd dust in ways that aren't intuitive. The point is, if the dust counter keeps reporting a steady environment over a long cruise, that's evidence that the outer solar system has more texture than empty space. Theory 3, boundary physics, where the sun's domain meets the galaxy. The heliosphere is inflated by solar wind pressure, but it's confined by the interstellar medium outside, particles, magnetic fields, and flows that aren't controlled by the sun. Where those two regimes interact, you can get layers, shears, and energetic particle populations that refuse to behave like a simple decrease with distance. Think of driving from a calm valley into a mountain pass. The wind doesn't just get weaker, it becomes chaotic because competing flows collide. The weirdness lives at the interface. And that explanation is satisfying, until the plot twist. Because even if the physics is rich, the spacecraft itself is becoming a constraint. New Horizons RTG slowly fades. Mission planners have to choose which instruments run, when to observe, how long to transmit, when to hibernate. So the most precious frontier is also the one you explore with a flashlight that's dimming. That's complication number 1. Complication number 2 is controversy, real scientific debate, not manufactured drama. Some New Horizons observations that look at the faint background sky connect to a bigger argument in astronomy: how bright is the universe after you remove the light from known stars and galaxies? Measuring that cosmic background, invisible light is notoriously difficult because your own solar system adds foreground glow, sunlight scattering off dust closer in. From the Kuiper Belt, New Horizons has a cleaner vantage point for certain kinds of measurements, because it's farther from the densest inner dust cloud. That's powerful. But it also means every leftover photon matters, and tiny systematic effects can swing conclusions. So when New Horizons data is brought into those discussions, it isn't always a neat victory lap. It's a careful, sometimes contentious process: subtract this, correct that, argue about calibration, compare methods, publish, respond, refine. So now the mystery deepens. Are we seeing mostly solar cycle history stretched across space? Are we mapping a dustier than expected Kuiper Belt? Are we watching the heliosphere's boundary behave like a dynamic, wrinkled weather front? Or is one part of the strangeness actually teaching us that our measurement techniques, our subtraction of foregrounds, need to be better? Here's the part that makes this personal for all of us: this isn't just about curiosity. The heliosphere is a radiation shield. Its shape and strength influence how cosmic rays reach the inner solar system. That affects satellites, astronaut exposure, deep space mission design, and the engineering reality of traveling farther. Dust isn't trivia either, dust is risk. Its shielding requirements, sensor health, surface erosion, and the long-term survival of spacecraft that we will one day send on decades-long voyages. New Horizons is giving us ground truth in a region where we usually rely on models. And as of the mid-2020s, that long, continuous record is exactly what makes it special. A single snapshot can be a fluke. A decade-long cruise is a dataset. Scientists around the world can compare it with other heliophysics missions and with theory, and slowly turn "the edge is weird" into "the edge has structure for these reasons." So let me put you on the spot, because I genuinely want to know what you think. If you had to bet, which explanation is doing most of the work? A. New Horizons is mainly reading delayed solar cycle ripples. B. It's revealing a surprisingly persistent dust environment in the Kuiper Belt. C. It's sampling boundary layer physics as the heliosphere blends toward interstellar space. And what observation, one measurement, would convince you to switch sides? The hopeful ending is that none of this is a dead end. It's progress. New Horizons is still returning data, still acting like a scout in the dark frontier, converting faint impacts and sparse particles into an actual map. And future heliosphere missions and fast escape concepts are being shaped by exactly this kind of frontier science: go farther, measure better, resolve the boundary, and understand the shield we live inside. But this isn't the only mystery hiding beyond the sun's light. Next up, we can talk about what it really means to cross the termination shock, why the heliosphere might have a tail, and how dust and plasma can team up to create structures we never see from Earth. Because out there, New Horizons is proving something simple and kind of beautiful: darkness isn't empty. It's just unmeasured, until a small spacecraft shows up and refuses to stop listening. Thanks for watching. Keep looking up, keep thinking big, and I'll see you in the next one.